let's do another one here. Here's the strangeness of this stuff. What you'd like, clarified in these books I've been reading is the following. All roots are surds. All surds are roots. Okay, so a surd is something that's irrational. Square root of 3, square root of 4 is not a surd. Other roots are possible, but generally all surds will be roots. How could you show that? Well, if you had square root of 3 times the square root of 3 times the square root of 4 times the square root of 4, those are in the coefficient space, namely I guess that's 12, and I can do something like this. I guess that'd be squared and squared there. And the slight catch here is that this will generate surd coefficients. And I call that a violation. So I'd have to tighten this up. I'd have to do something like that, in which case I still get 12, and now I get x minus the square root of 3, x plus the square root of 3, x minus the square root of 4, x plus the square root of 4, and I think that works. All the coefficients are there. So I can take surds if had some messed up surd like this, say, what is this a root of? What's the minimum degree? Of poly. Can you show that that's the root of something? Well, I think you can do that with an r here, and you cube that, right, and you get the fifth root of 5 minus the square root of 2, and then I guess, geez, it seems like you're stuck. Well, this, if you took something like this, I think Crystal claims there exists a rationalizing factor. Many terms. So if you had 1 over the square root of 2, the rationalizing factor, to simplify this, is square root of 2 over the square root of 2. That's where you see this in complex or college algebra. In this case, here's an example from page 193, where you're given something much easier. The sum of 3 square roots. And its rationalizing factor is square root of 2 minus the square root of 3 minus the square root of 5. Multiply this times this times all plus. You do all the sign variations. So there's a minus and a plus. There's a minus and a minus and a plus and a plus. And I think there's one more. Square root of 2 plus the square root of 3 minus the square root of 5. You multiply all those and you're supposed to get an integer. Now, if you said, okay, these are the roots, let's first of all, just for fun here, see if I can confirm that using our nifty calculator right here. So this on page 193 doesn't say what you get. He says that's a rationalizing factor. Sometimes he says what you get and sometimes he doesn't. So let's see if this is true here. So I take the square root. Oops, that won't work. Let's try this again. The square root, second square root of 2. This is easier to do on a physical calculator, minus the square root of 3 plus the square root of 5. So speed up a little bit here. Square root of 5, close it up twice. Okay, now I can hit that, and then I can take the, maybe I can take the answer times, and I can go get the previous. Let's see if this works. And I can modify that to 2 minuses. Okay, and then I can do that multiplication. Okay, and then I can take that answer and multiply it by this one up here. Now with two pluses. Not exactly fun task here, but let's see what happens. Plus, okay. All right, and then the final one, I take that and I multiply it by this one modified one more time to make it a plus and a minus. A plus and a minus, and this should be, I guess, an integer. Bingo, minus 24. All right, so that's the kind of thing where I did rationalize a radical, a simple one, 3 square roots. And I needed 4 things to do that, the original and 3 more. Meaning if those were roots, I'd need 4 roots, hence a quartic. But the catch is, with those roots, do the symmetric polynomials go to integers as well? When I, instead of multiplying them, when I add them, what do I get? And, well, can they be roots of a 4th degree? can they be roots of anything? It's the other thing you'd think that they'd have to be roots of something, of some degree, an integer polynomial, but, it doesn't strike me as completely obvious. Well, this is not going to sum to 0. These are the 4, 1, 2, 3, 4. I get 4 square roots of 2, bing, 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 bing. The square roots of 3 cancel, and the square roots of 5 cancel, so I get 4 square roots of 2, which would be the sum one at a time is a 4 square roots of 2, which is not an integer or rational. Hence, these are not roots of that quartic. Could they be roots of a different thing? Well, I have minus 24 here. That's what I got. So could I arrange minus 24 in a different way? And I can't arrange it with these roots. If I specify a 4th degree with a constant of minus 24, with these roots, it's not a solution. These are not the roots of my coefficient space being Q. I get an irrational coefficient. It seems that these are puzzles that should, somehow should be worked out. Now, notice that Crystal has 2 chapters on this stuff. A chapter 10, where I got that example, he calls them irrational functions, which is kind of funny because, college algebra books, modern ones, don't mention irrational functions. I think what they mention is radicals. I think that's the best gloss on his irrational functions. And all the stuff in here is with radicals. Here's on 193, that example. And he does another one. And apparently the general idea is you multiply all the combinations with minuses and pluses to get the rationalizing factor. Quite a bit more intense than what we do in college algebra and intermediate algebra. He does another one down here, and he waxes up with this stuff to a general theorem, which is kind of interesting. That the conjugate of some complex thing is the rationalizing factor. I'll leave it at that. Then he goes over here into chapter 11, arithmetical theory of surds. He defines a surd as an irrational with an index. I think it's a pretty good gloss. And he starts to, classification of surds, independence of surd numbers. And here he does a nice, interesting quote that looks pretty good. The theory which we have established so far for quadratic surds may be generalized and also extended to surds whose index exceeds 2. I think those are tautological. Be generalized, index exceeds 2. This is not, you could have the index exceeds 2 and the structure of it is nested and more complicated than a single nest, I think is how that might be glossed. That's a nested surd there. And let's keep on going here. This is not the place pursue the matter farther, but the reader who has followed so far will find the ideas gained useful in paving the way to an understanding of the delicate researches of Lagrange, Abel, and Galois regarding the algebraic solution of equations whose degree exceeds the fourth. It's supposed to be useful to know this surd stuff, and I think what you can, glean from this is that all integer polynomials, rational polynomials, have solutions in the surd space. And when you broaden surds out to rationals, square root of 4, call that a surd. And from there you get to using the constant that the multiplication of 5 surd things delivers the constant, and then to backwash those, saying they are the roots and looking at the coefficients you get. And as we noted, you do not get necessarily a rational polynomial that you're rationalizing your set of the original plus the rationalizing factors multiplied. It don't give you a polynomial. When do they give you a polynomial? What polynomial do they give you? What you'd like is some algorithm where you start with some gobbledygook, like I had that fifth root of something, cube root of a fifth root, blah, blah, blah. And you have an algorithm that generates the successful rationalizing factors that do form the roots, the integer of an integer polynomial. When does that take place? Is it chaotic? We don't know. I think that's maybe what, Galois is getting at, is you can't do it for the fifth degree. You can't start with, or 5 degree or greater, you can't start with presume a surd jobber of higher than 5 somewhere in it and get to any polynomial that has that as a root. You can't find the rationalizing factors, and even if you did, I think, according to Crystal, you might be able to find the rationalizing factors, but they won't be the ones that work in a polynomial. They won't be the roots of a polynomial that you're looking for. They'll be roots of a non-integral polynomial, something with a surd coefficient. If they're the roots of something with a surd coefficient, does that imply they're not the roots of an integer polynomial and hence transcendental? Maybe I'm right. I was thinking I was wrong with saying that some of these algebraic-like jobs are transcendental. But you read this and you do an experiment, and as far as I can tell in this book, he doesn't make a clear connection. I still have to read this a little bit more to see how these surds make polynomials, make the roots of polynomials. What polynomials? You'd like to see that concrete if it's possible. I would certainly think that it is possible to start with some messed up surd, as in the roots of a quadratic, and derive, as I think I did somewhere, a r squared, plus br plus c equals 0 from the root r. You get back to the quadratic. It's a root of. The solution specifies the polynomial. I tried that with, we'll do one just for the heck of it here. It's kind of trivial, but I have ax plus b equals 0. Subtract b from both sides. Ax equals minus b. X equals minus b over a. I start with the root is minus b over a. I multiply both sides by a. I get that, and I get ar plus b equals 0. I start from the root, and I get back to the polynomial. And I think you can also do this one pretty quickly. Minus b plus or minus, let's do plus the square root of b squared minus 4ac over 2a. You call that an r. Get 2ar equals minus b plus a square root job. 4a squared r squared equals b squared plus minus 2b a square root plus b squared minus 4ac, and you keep on going with this, and you should get a r squared plus br plus c equals 0. You get back to there. Try it with the cubic, try it with the quintic formulas, and conclude that it should be reversible. If it isn't, then you don't have a solution. All right, just kind of meandering here.